Good morning, dear students. How are you all? I hope you all are fine. We are resuming our discussion of the second chapter that was about measurement techniques. And the last thing we discussed was, if you remember, because it is the lapse of many days after which we are starting, it was the comparison between random and systematic errors. That was easy to recall some of the basic differences between the two types of errors were discussed. Let me quickly discuss what those main differences between random and systematic errors were. A random error it arises due to such factors as imperfections of human senses, variations in temperature, variations in pressure. Sometimes these variations are beyond our control. So random error occurs sometimes because of the combination of various reasons, and sometimes we do not have exactly the exact idea what is the main reason behind the random error. So this is that type of error which arises due to reasons beyond our control. The second thing we talked about this type of error was that although we cannot eliminate this error completely, but it is possible to reduce it. And we reduce this error. It can be reduced by averaging a large number of readings. So this is a very well-known technique in experiments in which we repeat several measurements, then we take their average. The idea behind is to minimize the error if it's of random type. Another important thing about random error was that it may be positive, it may be negative. That means it may be to the higher side of the accurate value, it may be the lower side of the accurate value, it may be slightly higher than the correct value, it may be slightly less than it. So it means it may have any value around the correct value. Let's say the correct value should be 9. So sometimes our due to random error it could be 9.2, sometimes it could be 8.8. So random error gives us values both above or below the correct value. If we compare all these things with the systematic error, we see that random error, whereas the random error, we are not sure the reasons, but in system error, we are always sure that there must be some fault behind it. This fault may be in the instrument, this fault may be in the technique. But whatever that fault, it may be completely eliminated once we detect it. If we know this is the error in the instrument, we can quantify that error, we can plus minus it, and we can make our final value absolutely free of any systematic error. So this is possible. And the third point that I talked about systematic error was that if you have a systematic error in the instrument or in the technique, all the values will be greater by the same amount or less by the same amount. That means we have the same error repeated in all our measurements. So even though there is random error in our measurements, due to the presence of some systematic error, all our values will appear to be affected by the same amount. So that means all the values appear to be higher above a certain value. So we immediately suspect that there is some kind of systematic error presented. And if we carefully check our instruments or technique, we can easily spot it. And once we spot it and quantify that error, we can get rid of it. We can completely eliminate it. So this is an overview of what we discussed last time. Today, we are discussing another small topic, but this is important, related to our next discussion, which is the main topic of this chapter. So this is about precision. Sometimes we are required to define precision and accuracy. In the daily day-to-day language, precision and accuracy are interchangeably used, and it is thought that these two terms have the same meaning: precision and accuracy. Before I define precision, I take you back to the discussion that we had when we started talking about the measurement of length using three different instruments: meter rule, vernier caliper, and micrometer screw gauge. If I make a measurement with the help of the meter rule, let's say I measure 10 centimeters with this. That means 100 millimeters. When I measure with the meter rule, I have to write it in this manner. If it's 10 centimeter, which means 100 millimeter, I have to write it 1 millimeter as the precision of this scale. This is the minimum possible measurement which we can make with the help of the meter rule. But if I compare it with the same measurement made with a vernier caliper, that should be 0.05 millimeter. This is with the vernier caliper. And if I make a similar measurement with a micrometer screw gauge, although we don't have 100 millimeter on it, let's say there are two, because it's possible to have 25 millimeter on it, so 25 plus minus 0.01 millimeter. So this part of the measurement, which I am writing alongside the measured value, this decides the precision of the scale. We can easily decide which of these three scales is more precise when compared with the other two. The size of the smallest measurement with the help of meter rule is 1 millimeter. Although even this could be inaccurate. If we try to measure 1 millimeter with the meter rule, this is not going to be a very reliable reading. But the smallest division on this scale is 1 millimeter. So we can say that 1 millimeter or 2, sometimes they write plus minus 2 here. But if I write the minimum, I can write 1 here. So 1 millimeter is something to do with the precision of the scale. But if I make the similar measurement with the help of a vernier caliper, this becomes 0.05 millimeter. That means the smallest division or the smallest measurement we can make with the help of vernier caliper is much smaller when we compare it with the meter rule. So vernier caliper is obviously more precise instrument than meter rule. But if we use a micrometer screw gauge, this part becomes even smaller as compared to this. This is 0.05, whereas it becomes 0.01. So this is 1/100th of a millimeter. So 1/100th of a millimeter makes it more precise instrument. This part that I have made, that I have written alongside the measured value, this brings us to another definition, and that is the absolute or actual uncertainty. Uncertainty means there is an inherent doubt in that scale. Whenever we make use of meter rule, there is definitely a doubt in all of its measurements, and the minimum amount of that doubt is 1 millimeter. It could be 2. They recommend that we write it 2 millimeter, but the minimum is 1 millimeter. If we use vernier caliper, it is this. This is the doubt in all its measurements. And if I use screw gauge, 0.01 is the uncertainty or the doubt in all its measurements. So actual or absolute uncertainty means it is that doubt which is the inherent part of all the measurements that we make with the particular instruments. Now I come back to the precision. An instrument or a measurement is said to be precise if it has a small value of actual or absolute uncertainty. So these two things are related. That means if I go on decreasing the actual uncertainty in a measurement, I'm measuring length. So instead of 1 millimeter, I make it 0.05, and if possible, I can make it 0.01. So I'm reducing the amount of doubt in the reading. So actual uncertainty is becoming smaller. And as the actual uncertainty becomes smaller, the precision of the instrument is improved. That means the instrument is more precise if its actual uncertainty goes down. So the final verdict is that an instrument or a measurement is precise if the actual uncertainty, if the actual or absolute uncertainty in it is small. So this is the precision. That means those expensive clocks, those expensive watches which claim that they can give you a time accurate to 1/1,000,000th of a second are highly precise devices, highly precise instruments, and that is why they are expensive. Now we come to the accuracy, how accuracy is different from precision. Let's say we have a very expensive watch which claims to give you a time accurate to 1/1,000,000th of a second. That is that is the precision of that instruments. It is accurate to 1/1,000,000th of a second precision. But due to some setting, let's say in the beginning, somebody has to set its time, and instead of 8 a.m., the time is set at 8 p.m. So this is highly inaccurate. Now it will show you a time, although it's highly precise, but it is accurate because instead of AM, it is showing PM. So it is exactly 12 hours lagging or leading the time. So that is the inaccurate measurement of time by that precise instrument. So there is some kind of error in it. So accuracy means how close the value, the measured value is to the accurate value. Whatever measurement in the instrument is showing how close it is to the accurate value is its accuracy. If it is 9.81 is the acceleration due to gravity, and your experiment shows exactly 9.81, this is highly accurate. But if it is 9.91, it is precise, but it is a bit inaccurate. If it is 10.01, it is still precise, but it is more inaccurate than the first reading. If it is 11.00, it is still precise, but it is more inaccurate now. So further you go from the accurate value, the smaller is the accuracy in your measurement. There is a relationship between precision and random error. Let me discuss that as well. Then I'll come back to accuracy again. Relation between precision and random error. Suppose there are two graphs given, and there are certain set of values taken on both of these, and students make the best fit in both cases. In one case, values of let's say this is a certain value x plotted against y, and this is what the graph looks like. One, two, three, four, five, 6 sets of readings. So you see the best fit line is carefully drawn with the 2 points on the line, 1 point slightly above the line, 1 point is slightly below the line, 1 point is slightly further away from the line, and this point is same distance below the line. So the best fit is the line which is exactly passing through the points. So we have equal number of points on the two sides. So best fit is shown here with the 6 points plotted. This is a small random error. Small random error. But if we have a situation similar to this, this is still a best fit line, because you see we have equal number of points on this side of the line, above the line, and same number of points below the line, and all the points are corresponding to each other. I mean, this is at the same distance from the line as this point. This is the same distance as this one, and this is the same distance as this one. So equal number on both sides of the lines with equal distances. That means the best fit is fine. But what is different in the two? Although this will give you the same result because the best fit appears to be same. But what is different is that in this experiment, the values have larger random error. Larger random error. So what if we have to decide whether the value that we have calculated is accurate and it has a large or small random error? There is another graph that we need to understand that. Sometimes we are required to interpret a graph in which the number of readings that we have taken are plotted with the values that we obtain. There are several readings that I have taken, several measurements that I have taken, and each value is giving me slightly different value, slightly different answer. So there is a spread. If the spread is very small, obviously I'll get a graph of this shape. This is a certain value x plotted against the number of times I have repeated the measurement. Sometime I get the value of x here, sometime here, sometime here, sometime here. And if I, let's say this is its accurate value x naught. X naught is the accurate value of x, and I have some values slightly greater than x naught, some values slightly less than x naught. And when I plot all these values here, I get a curve in this manner. This curve shows that I have a small random error because the spread is not very large as compared to this. Look at this. This graph shows that most of the values that I obtained in the experiment for this particular quantity, they are spread around the correct value. So this graph is accurate and precise because it has a narrow region in which most of the values are repeated. And this is something to do with this graph. Most of the values appear to be very close to the line, so it's a small random error. But whether they are close to the accurate value, I have to understand a graph like this. There is some correct value x naught, and I plot all these values. Let's say number 1 value that I obtain appears here. Number 2 appears here. Number 3 appears here. Number 4 appears here. Number 5 appears here. Number 6, if I repeat, let's say 1 is taken here because I cannot go beyond a certain number. So let's say 3rd and 4th values appear to be at the same point. So 3rd is here and 4th is here, right? So all these values, when plotted, they give us a shape of this graph. This is a graph which shows that it is a highly accurate and highly precise experiment because all the values are very close to the accurate value. They are not very, very far like this. So this experiment, although it will be considered accurate because the spread is it's maximum at the accurate value, but it has large random error. So large random error means it is not precise like this, but it can still be considered accurate because most of the values appear to be around x naught. But if I get a graph of this type, that means this is much further away from the accurate value. So although it is very precise, because all the values are spread about a particular value, this may be a certain value of x around which all the values are appearing again and again. So that is why the spread is not much. All the values are very close to each other, so the set of those readings are precise. But this is highly inaccurate because look at the gap between the accurate value and the value that we are repeatedly getting in this experiment. So this is highly inaccurate. So although precise but inaccurate. So accuracy is about how close your readings are to the correct value. Accuracy has to be something to do with a known accurate value. So if 9.81 is the known accurate value of the acceleration due to gravity, and we conduct an experiment to calculate its value as you do in the labs in the AS, if you get values like 9.71, 9.79, 9.80, you are close to the accurate value, and these values are precise to 1/100th of the scale, 0, 1, 0, 2, 0, 3. So it could be this kind of graph. But if all your values are close to 12.01, 12.09, 12.11, so it's greater than 9.81 by a certain amount, and the spread is around that value. So it's precise but highly inaccurate. So this was about precision and accuracy. Precision and accuracy are two main requirements for any measurements. All measurements in physics should be precise, should be accurate. So we cannot compromise on precision, we cannot compromise on accuracy. That is why we suggest certain instrument for one measurement, certain other instrument for another measurement, so the measurements are precise enough, they can be relied, they can be used for further calculation with the minimum doubt in those measurements. Now, one last thing, and that is what do we do with the actual uncertainty and how we decide the amount of error that this doubt causes in our measured values. I'll give you at least one example. More of it will be discussed in the next lecture, but I give you some idea today. Suppose I use a meter rule to measure a certain length, and that length is measured in centimeters. So 25.0 plus minus 0.2 centimeter. This is usually the manner in which we report our measurement with the meter rule. I have made a certain measurement, it is exactly 25 centimeter, and I also report the amount of doubt in that measurement. This time I have written it 0.2 centimeter, which is usually recommended instead of 0.1 centimeter, you write 0. If expressed in millimeter, of course, I write it 250 plus minus 2 millimeter. But this time I have chosen to write in centimeter scale, and you must have noted that both of these two are expressed in the same unit, centimeters. I write them first in this manner. You write sometime the brackets, sometime no need to use any bracket. You write it without brackets like this, and the unit is same for the two, the measured value and the doubt. And this doubt, as I have said, this doubt is the actual or absolute uncertainty in that instrument. Let's say there is another measurement we have made with the same scale, and this time it is 16.0 plus minus 0.2 centimeters. So I have written two lengths. Let's say one is L1, the other is L2. These two lengths are measured, and I want to know what is the difference between these two. The difference between these two is 25 minus 16. If I write it in full, I want to take the difference of these two. When I take the difference, this is 9 plus minus 0.4. Instead of writing it 0 here, because if I subtract this value from this and I write 9, I'm supposed to take difference of these two, which should give me 0. But remember, this is the first rule dealing with the actual uncertainties, that whenever you take the difference or you add two values, even if I add the two, like 0.2 plus minus 0.2, if I add these two, even then the doubt is added, because the doubt in one measurement is added to the doubt in the other measurements, and this is the total amount of doubt which is pronounced now, which is increased or enhanced uncertainty, and this is the uncertainty in the addition. This is the uncertainty in the addition, this is the uncertainty in the subtraction, but in both cases I have added the actual or absolute uncertainty. This example is just to give you the idea how the doubt in one measurement is going to affect our final value when we add that value to something else, when we subtract that value from some other value. So this doubt sometime gets doubled. So whatever scale, if I measure the length of a certain object with slightly different doubt here, maybe 0.3 there, so 0.3 will be added to this, but obviously it should be the same values. If I same quantities, length is to be added into length. Of course, it cannot be length added to area or volume. It has to be the same quantities added. But this could be done with a different instrument, and this could be done with different instruments. So precision could be slightly different, because this actual uncertainty depends on the scale. Some scales are very precise, some scales are not. So this shows that this is a reasonably precise scale. But what if I use a scale on which I do measure 25 centimeter, but instead of 0.2, it has a doubt of 0.5 on it. That means it's not as precise as this. So 0.5 will be added to 0.2, or difference will be taken if I'm taking the difference. But my final result will show 0.5 plus 0.2, that means 0.7. So uncertainties are added if they are actual type of uncertainties, but there are other types of uncertainties coming, they are not added in that way. We have to learn the formula for that. In the next lesson, we'll discuss all those things in detail. Thank you for today.